Our next speaker is Graham Smith, who's one of the leads of the Strong Lensing Science Collaboration and from the University of Birmingham. Thank you for coming all this way, but Graham, take it away.
Thanks for the opportunity. Great, so I am, as Gautam said, I'm Graham Smith from the University of Birmingham, and my aim today is to convince you that we need deep target of opportunity observations with the Virgo Rubin Observatory to make the first robust and unambiguous detection of a gravitationally lensed gravitational wave. Excuse me. And I particularly like to draw attention to the contributions of my team in Birmingham, in particular Matteo Bianconi and Dan Rajchanovsky, and I'll be highlighting their work throughout my talk today. Hopefully I will master how to advance the slides any moment now.
Try clicking on the...
Oh, do a click? Okay, great. So the basic idea is quite simple. We're familiar with very beautiful data from the Hubble Space Telescope and others, which have revealed for many decades now gravitationally lensed galaxies. And hopefully it's not too great a leap for you to imagine that galaxies such as the big giant arc up there, which was actually the first one discovered by Sukhel et al. Back in '87, is a plausible host for a binary compact object merger in that galaxy that is also strongly lensed and multiply imaged. And for me, about 5 years ago now, this stimulated the question or fascination with, well, could we actually detect these things? And so in some ways, this talk will summarize my latest thinking on that subject. Before getting into how we might detect them and how many there might be, let's just quickly highlight some of the science applications if we're actually able to achieve this. And if you think about the different aspects of strong gravitational lensing, we're talking about the formation of multiple images. And so you have signals separated in time because of the gravitational time delay. And so this effectively builds for free new grav wave detectors, and the ability of gravitational wave colleagues to test GR from measurements of grav wave polarization is very strongly coupled with the number of detectors in terms of constraining the polarization modes. And so this first detection could really drive a step change in these kind of tests. We're familiar on the electromagnetic side in terms of magnification with right from the very early days, gravitational magnification was helping us to push back the redshift frontier at which galaxy evolution studies were being done. And this is continuing today with the James Webb Space Telescope. And so it's a very direct analogy in terms of being able to push back the redshift frontier of studies of gravitational wave sources and their counterparts. The accuracy to which, precision and accuracy to which grav wave colleagues measure the arrival of grav wave signals is of order of a millisecond. So this implies that when we do detect a multiply imaged gravitational wave source, that arrival time difference will be measured to that same, of order of magnitude, that same level of accuracy. That sweeps all sorts of further complications under the rug, but it will be a nice problem to have to try to solve these other problems to capitalize as much as possible on such an amazing arrival time difference measurement. I'll also say something on time delays in terms of studying, making progress on kilonova physics from the second kilonova image to arrive. I'll touch on that towards the end of my talk. So we've mentioned magnification already. Magnification offers one way to detect, select candidate lensed gravitational waves. Several of us have done that already. And you basically have, by direct analogy with what we're familiar with in the electromagnetic spectrum, gravitationally magnified objects appear to be brighter and closer than they really are. One can also potentially select candidates by virtue of detecting multiple images that have overlapping posteriors, which is for me at least, is most easily visualized by thinking of the sky with overlapping sky localizations such as this. This is the latest candidate that's been found. We put it on the archive, well, Matteo put it on the archive a couple of months ago. It's completely consistent in our initial look with being two images of a lensed binary low mass lensed binary black hole at quite low redshift. We can't prove it. There's no electromagnetic counterpart, but it's an example of candidates that are found in this way. So one way to phrase this little equation, A, the strain amplitude detected by LIGO, mu, the gravitational magnification, and D is the degeneracy between magnification and distance when interpreting gravitational wave signals, or in fact, when interpreting electromagnetic measurements as well, except we detect flux, not amplitude. And so how to break this degeneracy, particularly in the context of lensing, which is about 0.1% of the sky is strongly lensed. It's a useful order of magnitude number to have in your head. And it's really challenging because when you look on the left plot, you see that the predicted location of lensed gravitational wave sources, the solid contours on the left, completely overlap with the population detected by LIGO in 03, or LIGO and Virgo, I should say, in 03, above 5 solar masses. When you look below 5 solar masses, you see that potentially an efficient way to select lensed binary neutron star candidates is to select them as having a high probability of having a compact object in the mass gap in low latency. Another question, particularly when you think of the trying to select candidates based on detection of multiple images, is how to overcome the way that grav wave detectors operate, particularly in terms of how often they're on. Their typical run lengths have been of order a year so far, and also they're typically on with all 3 detectors in 03 taking data of the required quality, typically for about an hour. So cartoon style, you can think of a grav wave run so far as an hour on, 20 minutes off, an hour on, 20 minutes off, and then completely shut down after a year. What happens if your next image of your candidate, you would actually miss it because it was in an off period? This is particularly a problem for lensed binary black holes because the predicted time delay distributions can be very long. Predicted arrival time differences can be very long, exceeding the length of a run, and also generally exceeding this coincidence segment time as well. The situation looks more promising if we look at lensed binary neutron star mergers. That's because they're more highly magnified, and here the predicted arrival time difference is a better match to both the duty cycle and the run length. The elephant in the room, let's name it, is angular resolution. So how do we overcome the huge mismatch in angular resolution between the angular scale on which the angular scale of the data that we need to detect strong gravitational lensing, which is of order an arcsecond, and the angular resolution of gravitational wave detections, which is of order 100 square degrees, say, and will continue to be so for the foreseeable future. Well, we know how to detect strong lensing robustly. It was done back in the 70s and 80s with optical data, first lens quasar, the first galaxy cluster lens that I've already mentioned. And so the way to do, we also know how to do gravitational wave science at arcsecond resolution. This is a very, frankly, a very lame attempt by me to summarize an amazing body of work done by a lot of people. But proving the connection between gravitational waves and electromagnetic counterparts for binary neutron stars is hugely influential, I think, in now designing strategies for detecting gravitationally lensed gravitational waves. So this all, so if you put all of this together and summarize the first part of my talk, I argue that the path to making a robust detection of lensed gravitational waves, overcoming the very low prior probability of lensing and the degeneracy between magnification and distance, is to select candidates in the mass gap as being candidate lensed binary neutron star mergers, to benefit from the relatively, but not disastrously, high magnifications, such that the time delays are better matched to the operation of the detectors, and to benefit from the great discoveries of 5 years ago, and to look for the kilonova counterpart to achieve the required angular resolution. That's all well and good. Sounds nice, very exciting, but there's some important questions. When might this be feasible? And will lens kilonova counterparts actually be detectable? And when we've answered these questions, what we've learned from that, how does that fold back into the kind of science that we can hope to achieve from detections like this? So this sets up the rest of my talk. This is as technical as it's going to get, but it is important to cover this briefly. To answer the first of those questions, we want to get a robust handle on the number of detections that might be available to be made, and the formalism for calculating the rates of lensed anythings is pretty well established, and schematically it looks like this. You need to have a good model for your source population. You need to know a cosmological model so you can populate, you know, the relationship between volume and distance and redshift. You need a model for the lensing, and you need to understand the sensitivity of your detectors. And the thing I'd like to concentrate on here is the model for lensing, because we're talking about multiple imaging here, and this means that our model for lensing, in principle at least, must be a model for the probability of multiple imaging. And that implies that we need to solve the lens equation, at least in principle. And that's really challenging. It becomes tractable if you assume that your population of lenses is very simple, such as basically an unbroken power law, often modeled as a singular isothermal sphere or ellipse. But in general, the lens population isn't like that. So what to do? Well, it depends on your science goal. And the science goal here, apart from perhaps the detection of Rubin's first lens supernova, as we were discussing at lunchtime, but the science goal of measuring H0 from time delay cosmography involves a golden sample. You want simple lenses, so why bother dealing with the complexity of groups and clusters? Okay? And so assume a simple lens model, go forth, predict. That's a different science goal though here. We might be able to do some of the similar science in the end, but the science goal here is to make that first detection, is to search for that needle in the haystack. So therefore we need an approach that's agnostic to the mass or complexity of the lens. And so that makes it even more, so the way to get around the complexity of solving the lens equation is to not solve it, is to make predictions in terms of lens magnification, which is a much easier thing to do and enables us to be agnostic about the lens. So if we put all of this together, then we come to a prediction of the magnification distribution of gravitational lens gravitational waves. I've shown the plot's a little bit busy. I've included trying to save space in a long paper to get it under 20 pages for monthly notices, so shoved quite a lot into this figure. But if you look at the black curve that I've highlighted with the arrow there, that shows you the predicted magnification distribution for lens binary neutron star mergers in 05. And you can see that it's peaking at about 100. And you see there's very little power at magnifications below 10. What that means, in summary, is that indeed this full range of lens mass is relevant, because both galaxies, groups, and clusters that tend to have flatter density profiles are all efficient at producing multiple images at magnifications above 10. And so this is the plot. This shows you the predicted rate of detectable lensed, well, binary black holes as well, but let's pay attention to binary neutron stars for now. And you see that in the mid-2020s, it starts to get interesting. Let's not put it any stronger than that. I would argue that we need to be ready, because we need to be ready to get lucky. Yeah? The rate is nudging towards 1 per year. The main uncertainty is the normalization of these curves. That's because of the uncertainties in the local co-moving rate. But it wouldn't be so surprising that the rate is about 0.1 per year in the mid-2020s. And the fifth run will last for multiple years, I understand. Yeah, so it starts to get interesting early in Rubin's life. It was great that Matt Nicol moved to Birmingham for all sorts of reasons, including that it made it very easy to collaborate on lensed kilonova light curve predictions. So this is the union of my lensing predictions and Matt's kilonova models from his paper in 2021. And we have the solid curve, the unbroken curves show you a 1708-17-like kilonova. The dashed curves show you a conservative model where let's not get so much into the physics right now, that early blue emission is turned off and there's a more typical viewing angle. And the typical magnifications, as we've seen in 05, will be 100. So if you pay attention to the lower dashed curve in each panel, that shows you the bottom end of the range for the magnification of 100 scenario. And you can see that if the observatory will tolerate us, we will be able to detect these with deep target of opportunity observations. And for this reason, spending that much time, it will also be very important to prioritize low, well-localized candidates. I'd like to come back and highlight Matteo's work a little more, because it is possible, as we've shown in his recent preprint, it is possible to tailor the light curve predictions and therefore the TO strategy to individual detections such that we are maximizing a chance of success, but also not wasting telescope time, only go as deep as we need to. And once we have the data, we need to know where to look. And so Dan's thesis has been about building an all-sky watch list of groups and clusters out to, let's say, approaching redshift 1 with existing infrared data, basically trying to find all of the groups and clusters, some of which all of which are capable of lensing, not all of which might be recognizable by background galaxies, before Rubin turns on, so that we're ready to go to filter the alert stream from day one. And his results look very promising. I'm starting to run out of time. This is my plot. Perhaps people are welcome to ask me about this. This highlights the opportunities in terms of time-delayed cosmography. Simon very helpfully pointed me to the Cremonesi et al. Paper, which points to the opportunity to break the mass sheet degeneracy from the grav wave data themselves, and also noticed that the predicted time delays are matched to the time scale on which we'll be getting on sky to try to detect the first image. So we don't need to, unlike ref style, potentially we don't need to predict when the second image will arrive. It will arrive while we're looking for the first one, which will present challenges in terms of angular resolution, but that's a problem I'm prepared to try to solve. I couldn't resist this for Gautam's benefit, who's about to cut me off. We prefer area over cadence, and one reason is that lens kilonovae, you did ask, lens kilonovae will be present, but quite rare in the Rubin alert stream. This is preliminary. It's another effort by Matt and myself, and without a rolling cadence, there'll be about 10 through the whole survey, one per year. That's rare, I think. Okay, at risk of offending Gautam further, I will close there and leave you with my summary. Thank you for your attention.
We have questions for Graham. I'm going to go to Federica right away.
Hello, thank you. I think I heard you say that the neutron stars' timescales are better suited to the observing schemes because they're more highly magnified, but I don't think I know or understand why they're more highly magnified.
That's in, where are we?
Yep.
Yeah. So basically, because at the relevant mass scale, even with help from lens magnification, the lens population are out there. It's kind of redshifts 1 to 2, and so you need more magnification to get there, right? So for 05, think lens binary neutron stars, high, and I said not disastrous, hundreds. You know, it's high, but it's not crazy. High magnification regime. All lenses are relevant. The binary black holes are in the in the low magnification regime of up to about 10. And so clusters are still relevant, but they won't be forming multiple images, right? So they will be magnifying at that level, but they won't be multiple. Cartoon style, but that's the general picture.
So extremely interesting stuff. So this is probably very basic because I haven't thought about this at all, but when you're talking about magnification of gravitational waves compared to EM waves, what we actually detect is the strain, which goes down as 1 over r in terms of the distance.
Yeah.
So in terms of magnification, do you get like a square root of the typical magnification that you would get? And so you don't magnify as much as you would for the EM waves, is that right? Because it's typically a square root?
Effectively, yeah. So that's the little equation. Yeah.
Yep. Yeah.
Yeah.
Okay.
Exactly. Yeah. So the short answer is yes, and the limiting factor for the detection, for the joint detection, is a LIGO sensitivity. So we get on that last slide, we actually find more untriggered lens kilonovae in the alert stream than you might expect if you were to just take a preprint on the joint detection at face value. I mean, it's still not many, but the basic argument is you need deep or deepish TOOs to find the grav wave detection triggered kilonovae.
I see Deep has a question online. Deep, go ahead.
Hi, I had a question on the slide where you had the two sky maps overlapped. I'm not certainly not an expert on the field of lensing, but from what I gather, it is that if we have strong lensing, then the waveform morphology does not change a lot. It's only a change in the amplitude, and so in effect, what we should have is an overlap of all the intrinsic parameters like the masses and the spins and so on and so forth. And I'm wondering here, since you've showed the overlap of the two sky maps, I'm wondering if you've also done a comparison of the so-called posterior overlap and hence conclude that this might be lensed.
Yeah, that's a great question. We've deliberately not done that. That's why I was careful to say that, in terms of the kind of simple analysis that we've done, it's a candidate. I assume that we have the co-chair of the LIGO Virgo KAGRA lensing group in the room. Maybe we might hear a more sophisticated analysis of these and other image pairs in their upcoming work. I don't know. But yeah, we haven't done that. We were actually looking for. So we followed these two up as candidate lens binary neutron star mergers, and as people may know, pretty much anything that had a high P gap in low latency did not, broadly speaking, did not remain there when the catalogue came out. So there are candidates there, but they, with the full parameter estimation by the LIGO colleagues, then they becomes more refined and things can change. But that's okay. It's a way of finding interesting things to look at.
Thank you so much.
No problem.
Thank you. I was just wondering if you also have plans for some automated search strategy in LSST, for example, to look for that?
I think the short answer is yes, and in collaboration with the group of us having lunch discussing strong lensing pipelines and transient detection pipelines and so on and so forth. Yeah. So yeah, good point. I better finish.
So we should move on and thank Graham again.